Hello everyone, my name is Chris Edwards and today we are going to write a SQL query. Our problem today is a fairly tricky one involving the combination of overlapping time spans. The facilities manager at a prominent music conservatory has a logistics problem. Toward the end of each academic year, graduating students must give a graduation recital as part of their degree requirements. These recitals take place in one of two recital halls, dubbed Hall A and Hall B, which must be booked in advance by the students' various departments, for example, piano, voice, brass, etc. Each department can book a hall for multiple days at a time, and multiple departments can book the same hall on the same day. On any day where a hall is in use at all, the facilities manager has to perform certain preparatory steps to make sure the hall is ready to use, for example, putting out chairs, double-checking the AV system, etc. So the manager needs to know when the hall is going to be in use. The manager currently has access to a database table called Recital Hall Bookings with the following structure. Each row contains the start and end dates of a reservation of a particular hall by a particular department. And while this data is helpful, it can be complicated to read at times. Reservations can overlap with each other in many different ways, and there can be duplicate reservations with the same start and end dates as each other. The facilities manager would really like a simplified report with only one row per continuous period of use per hall. In other words, every time there are duplicate or overlapping reservation time windows, the facilities manager would like to squash them into a single row. We need to write a SQL query to accomplish this squashing procedure. Now, because this is a bit of a tricky concept, I want to walk through the expected output here in a bit more detail than usual. The first row in the output corresponds to the piano department's booking of Hall A, which does not overlap with any other bookings in that hall. The second row encompasses the next three bookings of Hall A. The first of these bookings from the voice department starts on the 17th and goes through the 20th. The next booking from the strings department overlaps completely with the voice department booking. And finally, the third booking, the brass department's booking, starts on the 20th, which just barely overlaps with the end of the voice department booking mentioned earlier. Because of this chain of overlapping bookings, Hall A is in continuous use from March 17th through March 25th, and therefore all of these bookings get squashed together into the second row in our expected output here. Moving on to Hall B, the first expected output for Hall B combines the overlapping voice, woodwinds, and strings bookings from March 14th through March 22nd. And finally, the last two rows in the expected output for Hall B map one-to-one onto the last two bookings in Hall B, neither of which overlap with any other bookings in that hall. And with that, that is all the setup for today. If you want to have a crack at solving this problem yourself, there are links in the video description to this full problem statement and instructions on how to replicate this coding environment on your local machine. Feel free to pause the video now and come back later for a solution walkthrough, coming right up. All right, welcome back everyone. We will now take a look at a possible solution to this problem. So, as I said in the intro, I consider this a fairly tricky problem, and some of you watching this may not have even known where to start with this problem. And when I find myself in that situation, not knowing where to start, I sometimes find it helpful to look at the desired end result and then slowly work my way backward. So let's ask ourselves, what would be the easiest starting point from which to get this expected output? What would our input need to look like in order to make computing this final output very straightforward? Well, we essentially need to group multiple rows in our input together to produce an output at a coarser granularity than the input. And that is a perfect situation for a group by statement. it would be really great if we could just write a simple group by statement to collapse the many overlapping bookings in our source data into the squashed summary rows that we see on the left here. So let's try writing one and see how far we can get before we run into trouble. Now this is about as far as I could get. I know we need Hall in our output, and I know that we will be constructing these squashed rows with the earliest booking start time and the latest booking end time for each continuous period of use. So I got that much down. Where we run into trouble is deciding what to actually group by. What we need here is some mystery column that has a different value for each continuous period of use for each Hall. For example, let's say that instead of this data right here, let's say our source data looked like this instead. If we had this group ID column here, we could just group by Hall and group ID, and we'd be done. The first booking of Hall A is the only booking with group ID 0, so it would get its own row in the output, just like we want. The next 3 bookings in Hall A all share the group ID 1, so they would all get squashed together into a single row in the output, again, just like we want, and so on. Having this group ID column correctly populated would solve all of our problems. But unfortunately for us, we don't have this column. So we should ask ourselves, can we make this column? What SQL query can we write that would assign unique group numbers to each overlapping chain of bookings in each Hall? Well, that in itself is actually a fairly tricky problem. So let's start even smaller. Another trick I like to use is to solve a simpler version of a problem first and then build up to the harder version of the problem. So what if instead of uniquely identifying each overlapping booking group with its own ID, we instead just try to identify when each new group begins? In other words, we need to figure out what the criteria should be for when a booking should join an existing group versus when it should constitute the start of a new group. So let's consider some candidate logic, and it helps here to think of the bookings in chronological order. One possible rule would be if the current booking's start date is after the previous booking's end date, then the current booking is the start of a new group. If we consider Hall B for a moment, this logic actually seems to work pretty well. By this logic, the voice, woodwinds, and strings bookings in Hall B would all form a continuous overlapping group, and we would need to start new groups for both the brass and piano bookings, since both of their start times are strictly later than the end times of their immediate previous bookings. However, this logic falls apart a bit when considering Hall A, specifically the brass booking in Hall A. By our current rule, this would constitute the start of a new group, since the brass's start date, March 20th, is strictly after the previous booking's end date, March 19th. However, the brass booking does overlap with the voice booking 2 rows before. This overlapping group has a different structure than the one from Hall B, since in this case we have this initial booking that then overlaps with multiple subsequent bookings, which in turn do not overlap with each other. So it's a little trickier. We clearly need to evolve our rule slightly. It's not enough to consider the end date of the immediately preceding booking when deciding if there's an overlap or not. We need to consider the end dates of all previous bookings in that Hall. More specifically, our new and improved rule should be, if the current booking's start date is strictly after the latest end date among all previous bookings in the current Hall, then the current booking is the start of a new group. This rule works in every case, including our tricky situation in Hall A. So now that we have a decent rule, we need to translate it to SQL. We need to make a new column that somehow indicates which rows are the start of new groupings using a comparison. We need to compare the current booking's start date against the latest end date among all previous bookings. Well, we have the current booking's start date. That's just the start date column in our source data. But how do we get the latest end date among all previous bookings? There are a couple ways to do it, including some gnarly self-joins, but there is a very elegant solution using window functions. If you've seen my previous video about the rolling average of Sisyphus, you know about window frames and the ability that we have to define custom frames if the situation calls for it, and this is one of those times. We can define a custom window frame that encompasses all bookings in the current haul before the current booking, and then use the max function to get the latest end date from that window. You can see here we get the max end date. We partition by haul so that we can only consider bookings in the same haul as the current booking. We order by start date and end date to ground our window definition in the chronological order of the bookings. And then we set our window frame to rows between unbounded preceding, meaning from the beginning of the partition, and one preceding, meaning the window stops just before the current row. And if we run this, you'll see we now have a working indicator column that contains a 1 whenever the row constitutes the start of a new group in the current haul. So now we have solved the easy version of our problem. We can return to the full problem. How do we assign unique group numbers to each overlapping booking group? Well, fortunately, this actually turns out to be pretty easy to add on to what we've already done. We have constructed this group change indicator column that contains a 1 whenever a new group starts. So if we were to just take a running total of this indicator column, that running total will naturally increment by 1 every time a new group starts, thereby giving that new group a new group ID. We just need to wrap our change indicator query in a CTE and then apply a sum window function on top of our group change indicator field. And if we run that, there we have it. We have come full circle and created the group ID column that we wished we had in the beginning. And we already know exactly what to do with it, thanks to our little stub query from earlier up here. We just need to wrap our group ID query in one more common table expression, plug it in to our stub query, and we should be done. And sure enough, our output here exactly matches the expected results on the left, and we are in fact done. Before I leave you, I did want to bring up one other interesting way to think about this problem. If you have studied academic computer science, or even if you have just done some data structures and algorithm study in preparation for interviews and the like, you may be familiar with graph theory. And in graph theory, there is a well-known problem of finding connected components in an undirected graph. The problem we just solved is actually just a variant of that connected components problem. You can construct a graph where the bookings are the vertices, and there exists an edge between two vertices if the two bookings' date ranges overlap each other in the same haul. If you model the problem like this, finding the groups of overlapping bookings is equivalent to finding the connected components in this graph. Now, I tell you this because I think it is interesting to conceptualize problems in more than one way. But from a practical perspective, I would reach for the solution I've spent this whole video describing well before I would try to write a version of the connected components algorithm in SQL. I think you could do it, probably using a gnarly recursive query of some kind. But I think this window function-based solution we've discussed today is a much nicer, more idiomatic way to tackle this particular problem in SQL. And this solution is really only possible because of the special constraints this problem has that differentiate it from a generic connected components problem. Specifically, the chronological dimension, the ability to meaningfully order the bookings by date and consider bookings that happened before the current one. All that lets us write a more efficient, more elegant solution in SQL compared to what it would probably take to write the generic connected components algorithm. To be perfectly honest, if I ever found myself in a situation where I did have to solve a generic connected components problem, I would almost certainly try to keep that in the application layer using a programming language like Python. I would not reach for SQL as my first choice there. All right, well, that is it for this video. Thank you all for watching. If you have any further questions about this problem, or if you think of a different approach to the solution that I may not have considered, please let me know in the comments, and be sure to subscribe for more SQL query writing content in the future. Until next time, happy querying.